So this is Dr. P. My name is Dr. P, and I thought I'll make a short video trying to explain what a derivative is in the simplest possible way to understand what the derivative of a function is. So the entire calculus process is based on this idea of limit, the derivative, and the integral, right? And so it's very important that we actually know what a derivative is. So, putting it simply, let's look at this scenario. Suppose we have a car which is traveling along a road, right? Okay, and we want to find the velocity of the car at, say, 11 o'clock. Okay, sharp at 11 o'clock, not between 11 and 11:15, not between 11 and 11:30, but we want it perfect at 11 o'clock. How do we do that? The trick there is actually because we want it at 11 o'clock, right? There is no time change because the time is fixed at 11. So how do we achieve a velocity without a time change? This is the most fundamental question about the derivative. All right. But essentially, what happens is, right, the derivative actually measures the rate of change. It could be a car traveling, it could be the profit function of a commodity, something which is changing. We want to find the rate of change at a given point. That is what the derivative does. So let's look at this example now a little bit more carefully, right? So suppose we have an object moves so that after x seconds it has traveled a distance x s of x equals x cube. So just imagine it's a car or something that is traveling. So after x seconds it has moved x to the power 3. What does that mean? So suppose we want to find out after 2 seconds how far has this car moved. Then what you do is you go up here, put x equals 2. You get what? 2 to the 3, which is 8 feet. Okay, now suppose you want to find out how far the car has moved after 4 seconds. What you do is you go and put x equals 4 here, you get 4 to the 3, which is 64 feet. So by plugging in different values for x, right, different times for x, we can actually find out how far it has traveled during that time. Okay, so now suppose we want, our target is we want to find the instant velocity after x seconds. Okay, so after at x seconds, we want to actually to find out the instant velocity. And then how do we do that? Well, first of all, the biggest problem is we want to find the velocity. We have to let it move a little bit because we know that at least the average velocity that we learned in high school is what? Change in distance divided by change in time. So you're dividing by change in time. There has to be a time change. But now we want to find the instant velocity at x seconds. Not slightly after x, but at x, at x. There's no time change. How do we achieve this? So what you're going to do is we are going to make a small time change called h. So now we were at x seconds. Now we move the time to by a small amount. Now the new time is what? X plus h. So how long has it traveled in the new time? What you do is you go up here and replace x by x plus h, and then you get x plus h quantity to the power 3. So x plus h quantity to the power 3. This is your new distance traveled. And this is the old distance traveled, right? This is the time, the distance traveled after x plus h seconds. This is the distance traveled after x seconds. So what is the change in distance from x to x plus h seconds? So in the h seconds, h additional seconds, how far did the object travel? What you do is you take the new distance, which is this, subtract the old distance, which is that. So the change in distance between x and x plus h is this. What's the change of time? Well, only h seconds have passed between the two places. So change of time is h. So what is the average velocity between x and x plus h? So we know that the average velocity is the change of distance, which is what? This, right? Or this in a more general way, right? Over the change in time, which is what? H. So this is the average velocity. But that's the average velocity between x time x and time x plus h, a small change. But that's not what we want. We want to find the instant velocity at x, not between x and x plus h, but we want to find the instant velocity at x. How are we going to do that? The only way we can do that is to make h, our time change, smaller and smaller and smaller, so that the time change is so small that x and x plus h are almost together. Almost. But not coinciding. Why? Because if it coincides, then there is no time change. So the whole idea is we do what is called the limiting process. What we're going to do is to make h gigantically and very infinitesimally small, right? So that this becomes very small, so there is hardly any time difference. So this process is called limiting, and we will learn more of that. You will learn more of that during your calculus course, but my job today is to show that when you take the limit as h, the time difference going to zero, the average velocity, which is this, will limit to the instant velocity at x. So once again, this is the average velocity between x and x plus h. If you take the limit as h tends to 0, then the average velocity becomes the instant velocity at x. For example, if you take 11 o'clock, you want to find the instant velocity as 11 o'clock. If you take the average velocity between 11 and say 5 seconds past 11, that could be a good approximation for the 11 o'clock velocity, but no, because a lot of things can happen between in these 5 seconds. So you make the 5 seconds smaller and take the average velocity between 11 and 1 second. Could be better, but still a lot of things can happen between 11 and 11 plus 1 second. So we need to make that time smaller and smaller, and we really need to make it limit to 0. So this limit is very important. This is a whole basis of calculus. So this is limit was found by Newton, and then this is how calculus all began. So, and then we have another name for that. It's the instant velocity. It is also called the derivative of the distance function. Here distance is changing, so it's the derivative of the distance function, and we also denote it by s prime x. S6 is the function, and s prime x is the derivative. We have another name for that, and that is ds over dx. So it's kind of like a small change in distance over a small change in time. Can you see? Okay. So this limit is very important. That is called the derivative, right? And that is this limit. So by using, so when you do your calculus course, you will learn how you will get to know different tools which will help you to find this limit, and you can actually show that this limit is equal to 3x squared. Okay, so the derivative of x cubed is 3x squared. But hey, if you want to find the derivative, and every time you want to find the derivative of a very complicated function, if you try to find this limit, it's going to be a very difficult affair. So we have rules to help us find these derivatives. So what we are going to do during this course is that we are going to learn some of these rules. Now we can actually get an idea of us for the first rule that we are going to do. So if you look at x cubed, look at the derivative 3x squared. It's almost like the power x3 has come down and the exponent 3 has become 2. This is actually a rule. It's called the power rule. And that is the very first rule that we are going to learn. We are going to learn how to find the derivative of a power, a sum, and then product and quotient and chain. And then we are going to do all that, and we will learn how to find this derivative. But remember, the derivative is the rate of change of that function. It could be the velocity of a distance function or the profit growth rate, but the rate or the rate at which the coronavirus is growing at a certain time, right? It's always the rate at a particular point, and that is the first and central idea of derivatives. Thank you very much for watching this.